secondary indeterminate forms. In this lesson, we will be evaluating limits of expressions that would initially lead to having a 0 times infinity or an infinity minus infinity form. At the end of this lesson, you should be able to evaluate the limit of such expressions by using L'Hopital's rule. Let us recall that one of the secondary indeterminate forms is the 0 times infinity form. We encounter this case whenever we have two functions, f of x and g of x, such that the limit of f of x as x approaches a is 0, and the limit of g of x as x approaches a is one that increases without bound. Thus, the limit of the product f of x times g of x as x approaches a would be of the indeterminate form 0 times infinity. Now, to evaluate such limit, what we need to do is first to transform the product f of x times g of x into an equivalent fraction that would give us initially a limit of a 0 divided by 0 or an infinity over infinity. So that in this case, we can now apply L'Hopital's rule. So what we're saying is that the limit of the product f of x times g of x as x approaches a whenever would be of the indeterminate form 0 times infinity would be transformed to the ratio of f of x divided by the reciprocal of g of x, evaluating the limit as x approaches a. If transformed to this ratio, the limit may be of the 0 divided by 0 or infinity over infinity form, so that we can now apply L'Hopital's rule in evaluating the limit in terms of the limit as x approaches a of the derivative of f of x divided by the derivative of the reciprocal of g of x whenever this limit exists. So if there is a limit to this expression, that would be the limit to this expression here, and therefore would be the limit of the given product. Okay, let us have now an example. Let us evaluate the limit of x, ln of x, as x approaches 0. So for this given expression of x ln of x, the limit as x approaches 0 would be in terms of 0 times ln of 0, or we have 0 times ln of 0 is not defined, but as x approaches 0, the value of ln x would be approaching negative infinity. Hence, initially, the limit would be of the form 0 times infinity, which is an indeterminate form. So what we need to do now is to transform the product x ln of x into an equivalent fraction, where the limit will be either a 0 over 0 or an infinity over infinity. So what we did was to rewrite or transform x ln of x into ln of x divided by the reciprocal of x. And evaluating the limit of this expression as x approaches 0, we will have it in terms of ln 0 divided by 1 over 0, or this will be of an undefined value, assuming the form infinity over infinity. Again, this is an indeterminate form, but it is of the form wherein it is valid to use L'Hopital's rule. Hence, we now apply L'Hopital's rule, evaluating the limit of ln x divided by 1 over x as x approaches 0, in terms of the limit as x approaches 0 of the derivative of ln x divided by the derivative of 1 over x. So for ln x, the derivative is 1 over x, and for 1 over x, the derivative is negative 1 over x squared. So when we evaluate the limit of this ratio as x approaches 0, then it is the same as evaluating the limit as x approaches 0 of 1 divided by x times negative x squared, simplifying this product to just a negative x. And using this now as basis to evaluate the limit as x approaches 0, we will have the limit equal to 0. So by L'Hopital's rule, the limit of ln x divided by 1 over x will be equal to the limit of this expression here, or simply the limit of negative x as x approaches 0, which is 0, which in turn would be the limit of the product x ln of x as x approaches 0. Okay, let us now look at the case of having an infinity minus infinity, another indeterminate form. We will be able to encounter this case whenever we have the limit of f of x as x approaches a is unbounded positively, and the limit of g of x as x approaches a also will be increasing without bound. So the limit of the difference f of x minus g of x as x approaches a would be equal to the difference of the limit of f of x as x approaches a minus the limit of g of x as x approaches a, or we have an infinity minus infinity. Again, before we can make use of L'Hopital's rule, we need to transform this difference into a ratio that would lead us to a limit either of the 0 over 0 or infinity over infinity form. Okay, so transforming from a difference into a fraction is required. Okay, let us have an example illustrating the infinity minus infinity case, evaluating now the limit as x approaches 0 of 1 over x squared minus the reciprocal of the product x squared secant of 2x. The initial investigation of the limit of the difference would lead us to having 1 divided by 0 minus 1 divided by 0, or an infinity minus infinity, an indeterminate form. So what we need to do now is to transform the difference into a fraction. Okay, so working now with the given expression, the first thing that we do is we apply the identity, a trigonometric identity, to secant of 2x, and 1 divided by secant of 2x is just equal to cosine of 2x. So the second term is transformed into this ratio. Now, having done this, what the next step would be to combine these two terms into a single fraction. And since we have similar fractions there, then we simply have in the numerator the difference of 1 minus cosine of 2x divided by the common denominator of x squared. Now, using this and trying to evaluate the limit as x approaches 0, the limit would be of the 0 divided by 0 form. Okay, and as such, because this is now of the 0 over 0 form, we can now make use of L'Hopital's rule to evaluate the limit. So what we have now is the limit of the derivative of 1 minus cosine of 2x divided by the derivative of x squared, evaluating the limit as x approaches 0. And as to the derivatives, for the numerator, we will just have a 2 sine of 2x, and in the denominator a 2x. Okay, now with this new fraction here, let's try to evaluate the limit as x approaches 0, and that would now result to a 0 over 0. Is still an indeterminate form. Now remember, we said last time, for as long as the limit of a ratio is an indeterminate form, you can always apply L'Hopital's rule. So here we apply L'Hopital's rule the second time, and we work with the limit as x approaches 0 of the derivative of sine of 2x divided by the derivative of x as x approaches 0. And as to the derivatives, we will have 2 cosine of 2x for sine of 2x and just 1 for the derivative of x. So that we simplify now this, try to evaluate the limit as x approaches 0 to having a 2 cosine of 2 times 0 divided by 1 or we just have a 2, I mean. Okay, we'll have 2 times 1 equal to 2. This one will give you cosine 0, and cosine 0 is 1. So at this point, we have the limit of this expression, which initially is indeterminate, is found to be equal to 2. Okay, then we said whatever is the limit of this expression will be the limit of this one. So the limit of this also will be equal to 2, which is also equal to that limit or to this limit. Okay, so concluding now, the limit of 1 over x squared minus the reciprocal of x squared times secant of 2x as x approaches 0 would be equal to 2. Okay, let us have a recap of what we have discussed. That the limit of an expression that initially would result to any one of the secondary forms 0 times infinity or infinity minus infinity can be evaluated by first transforming the expression to a fraction whose limit is either a 0 divided by 0 or an infinity over infinity. And as such, we can now apply L'Hopital's rule. Okay, so that will be all for today. I will see you in the next lesson.